Why do you have to add salt to an ice cream maker? Can't you just do it with ice? Anybody tried that? It doesn't work. It doesn't work with just plain ice. The reason we add the ice is because, adding the salt, is the salt lowers the freezing point. And it actually makes the ice colder. Milk will not freeze at 0 degrees Celsius, even though it's mostly water, because it has a bunch of stuff in it, fat and sugar and various things. And so the freezing point of the ice cream is lower than 0 degrees. So freezing point depression, nothing to do with mental state or being depressed because it's cold in the winter in Minnesota. Freezing point depression is a colligative property. There are several colligative properties. Colligative property means that it depends on the number of particles that are dissolved in the solution. It doesn't matter what they are. It's just the number of particles. So when we look at electrolytes versus non-electrolytes, what does an electrolyte do when you dissolve it in water, for instance? It dissociates. It separates into ions. So one formula unit of sodium chloride makes 2 ions. That makes 2 particles. So electrolytes have a bigger effect on colligative properties than non-electrolytes do, because they separate into more than 1 particle. Another colligative property is vapor pressure lowering. And so this is the one we're going to look at first. Let's just look at this beaker. So here we have a beaker with a watch glass, and we have a liquid here. Let's just call it water. And we've talked about this, that the water evaporates, even at room temperature, and then the gas molecules bounce around and they collide and they get trapped. And we get an equilibrium. And the pressure in this space here of the water is the vapor pressure. And that vapor pressure depended on the temperature of the solution. And for different substances, it depends on the intermolecular forces. But here we have the dynamic equilibrium. So if we throw some salt in there or sugar or some other foreign particles in there, this is going to interfere with the evaporation of water. It is not going to interfere with the recondensation of the water. These gas molecules are still going to condense at the same rate, because the fact that there's extra particles in here doesn't matter. But these particles in the solution get in the way of particles evaporating. They occupy some of those surface positions, and the water can't get to the surface, so it can't evaporate. So if the rate of evaporation is slower, then, and the rate of condensation continues at its same rate, then once you get equilibrium, you're going to have fewer gas particles, and you're going to have a lower vapor pressure. Does that make sense? This is really trippy. So that part most people don't have a problem with. This is really trippy. So if you take a beaker uncovered with pure solvent in it, and you take a beaker with a concentrated solution, so maybe really salty water, and you put them in this cake plate and cover them so that they can't escape, and you come back later, the solution level in the salty beaker will be higher than in the pure water beaker. Like, what? What the heck? Entropy, the spreading of energy. So now we don't have, this is similar to osmosis. We do not have particles going through a semi-permeable membrane, but we have a higher rate of evaporation in the pure solvent beaker and a lower rate of evaporation in the salty beaker. So these gas particles evaporate, but now they're free to go throughout this whole cake platter. And so they're going to bounce around. Some of them will get trapped here again, but some of them will get trapped here again. And when they're trapped here, the rate of evaporation is less. And so we'll end up with a net addition of water molecules to the salty beaker. Any questions? You could try that at home. I don't have a cake plate, but I should try that sometime. Of course, we have equations that describe these things. So Raoult's law quantifies the vapor pressure. So this law says that the partial pressure of the solution equals the mole fraction of the solvent times the pressure of the solvent when it's pure. So P0 is the vapor pressure of the pure solvent. So the vapor pressure is going to be directly proportional to the amount of solvent in the solution by moles. It's the number of particles that matter. So if we're interested in the vapor pressure lowering, how much does it become less? How much is it lowered? Then the change in pressure is equal to chi of the solute, the mole fraction of the solute, times the original pressure of the pure solvent. And there's a mathematical derivation there. I didn't put it up here because I'm thinking most of you are probably not interested. Did I guess right? I'm not going to commit. Okay, so we need to be able to do problems with this. So calculate the vapor pressure at 25 degrees Celsius of a solution containing 55.3 grams of ethylene glycol and 285.2 grams of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. So if we want the vapor pressure, we're going to use Raoult's law. So the vapor pressure of the solution is the mole fraction of the solvent times the original partial pressure of the solvent. So the partial pressure of the solution is going to equal chi for the solvent times P0 for the solvent. This 23.8 torr, that is the P0. That's the partial pressure at this given temperature of the pure solvent. So what do we have to calculate to put in here? We need chi solvent, the mole fraction of the solvent. So chi solvent equals the moles of solvent. What's the solvent here? Water. So it's the moles of H2O divided by the moles of everything in there. The moles of H2O plus the moles of ethylene glycol. I'm going to call that EG because it's too long. Well, how many moles of water do we have? 15.8? That sounds about right. How'd you figure that out?
285.2 grams of water divided by 18.02 grams.
Yeah. 285.2 grams of water divided by the molar mass, 18.02 grams. So then we've got the 15.8 down here. Anybody figure out what the moles of ethylene glycol are? Nobody wants to do that. 1, 2, 3 carbons, 12.01 times 3, plus 2, 4, 6, 8 hydrogens. And 2 oxygens. So molar mass 76.094. Grams per mole. And we're starting with 55.3 grams. So 55.3 divided by 76.094. 0.72673 moles. 72673 moles. So we've got 15.8 divided by the quantity 15.8 plus 0.72673 0.956. If we're considering significant figures, when we take this 15.8 and we add this, here the, we should actually have 4 sig figs on that. 285.2 divided by 18.02. 15.83. So that's 2 decimal places on that one. And then when we add this one has 3 decimal places, so it's going to end up being 2 decimal places. We can tell it's going to be greater than 15, so that's actually going to have 4 significant figures on the bottom and 4 on the top. And so it should be 0.9560. And that has no units. Yeah, sorry, I had a brain fart. So chi solvent is 0.9560, and P0 is 23.8 torr. .8 torr. I'm going with 3 sig figs because the vapor pressure here had 3. The unit is torr because that's the unit that the vapor pressure was given us. Mole fraction doesn't have a unit, so whatever this pressure is in, that's the same unit that the final pressure will be. Any questions? Because the solvent, in terms of numbers of particles, is 95.6% of the whole solution, then the pressure is 95.6% of the pressure it would be if it was pure water. What does volatile mean? It evaporates easily. So if our solute is volatile, if we're putting ethylene glycol, which is not volatile, or if we're putting sodium chloride into water, they don't have a significant vapor pressure of their own. But what if we put something like ether or alcohol in the water? They have a significant vapor pressure. In fact, their vapor pressure is higher than water. So if the solute is volatile, its vapor pressure is going to contribute to the vapor pressure of the solution, and the vapor pressure can actually be higher than the solvent by itself. So an ideal solution will follow Raoult's law at all concentrations for both the solvent and the solute. And if we want to know the total pressure above, the total pressure will be the pressure of the solvent plus the pressure of the solute, or whatever the components are, pressure from each of them. A lot of solutions, though, are non-ideal. They don't follow Raoult's law at all concentrations, and that can be due to solute-solvent interactions that are either stronger or weaker than the solvent-solvent interactions. Depending on the relationship that the solute and the solvent has, it can make things more volatile because they don't like each other and people want to get out. Or it can make it less volatile because they do like each other and their interactions are strong, and so they're going to tend to stay in the solution. So here's a graph showing vapor pressure versus mole fraction of A for an ideal solution. Here's the partial pressure of A, and it's a straight line. Raoult's law predicts a straight line. Here's the partial pressure of component B. Again, we have a straight line. As we get more and more A and less B, the pressure of B goes down. The reason that these are not the same, they don't start at the same point, is because the vapor pressure here of B is higher than the vapor pressure of pure A. And so an ideal solution, you just take this pressure plus this pressure at any given mole fraction, and you can predict what the vapor pressure of the whole solution is. If we have strong solute-solvent interactions, then that is going to reduce the vapor pressure of each component in the middle. Because the solvent and the solute are attracted to each other, and so their rate of evaporation is going to be less. And so you'll get this big sag in your vapor pressure solution. If the solute-solvent interactions are weak, then they're not enjoying being together, and they're going to evaporate. They're going to get out faster than if they weren't together, and then this gets bowed up. Yes?
So which one was for the glycol? The one in the middle?
For the glycol,
The one with the previous one?
we didn't comment on the interactions, but it's probably more like this one.
Oh, okay. So why does that help to keep the wire from boiling?
Well, we're talking about,
For the radiator.
yeah, you put ethylene glycol in your radiator to lower the boiling point. And we're going to talk about that. The vapor pressure leads into that.
Is this related to the intermolecular forces as well, like iron dipole?
Yes. So the solute-solvent interactions are intermolecular forces. And so if you have, if you have like two substances that both have hydrogen bonding, and they're going to be very attracted to each other, versus maybe a polar substance with something that has hydrogen bonding and they're not as attracted to each other, and so it'll vary.
Stronger the intermolecular force, the more bowing. Maybe from that.
Yeah, if the stronger these interactions, the more bowing you get. And the weaker those interactions are, the more bowing in the other direction. But there's a limit, of course, because if the interactions between these are so weak, they may not form a solution at all.
Totally that.
Well, one might totally evaporate, or they just might sit in separate layers. And we are not mixing together because we don't like each other. Oh, this problem.
You don't like it?
I don't like it. There's part A, and there's part B, and there's part C. I don't want to do it right now. Maybe later. Okay, freezing point depression. We need to make ice cream. Freezing point depression and boiling point elevation. So we just talked about vapor pressure lowering. That occurs at all temperatures. So here's our phase diagram. I almost lost the name of it. Our phase diagram. And so we learned that the pressure at which something boils the temperature at which something boils is where the vapor pressure equals atmospheric pressure. So if we look here, here's our liquid, here's our gas. So here, when the pressure is 100, when the pressure is 1 atmosphere, where this line between this evaporation line, where that crosses 1 atmosphere, that tells us what the boiling point is. Okay, so pure water boils at 100 degrees Celsius. So here's our vapor pressure curve, essentially. It gets lowered when you add a solute. So the solution, the pressure is lower. Well, what does that do to the temperature where the pressure is equal to 1 atmosphere? It makes it a higher temperature. The boiling point elevates. And this would correspond to the freezing point, and the freezing point is lowered. So what happens when you add a solute to a solvent is the region in which it remains a liquid expands on both sides. I used to have a hard time remembering which one got bigger and which one got smaller. I knew there was elevation and depression, and there was boiling point and freezing point, but I couldn't remember which it was. They separate from each other. So the temperature range over which it's a liquid now is larger. Okay? So the freezing point goes down and the boiling point goes up. So The result of the vapor pressure lowering is that you have a lower melting point and a higher boiling point. So of course we can quantify this as well. Freezing point depression is given by this equation. So the change in the freezing point, not the new freezing temperature, but the change in the freezing temperature, equals the molality. This is like the only place I can think of where we use it. The molality times a constant. It's a freezing point constant, and that will be for the particular solvent. So the change in freezing point is generally reported as a positive number because the molality and the freezing point depression constant are both positive numbers. But we understand that freezing point depression means that the temperature goes down. Here's a table of freezing point depression constants, and they're going to have units of degrees Celsius per molal, because you multiply them by the molality and that gets you a temperature. And then the boiling point constant, elevation constant. And so here we're given the normal freezing points and the normal boiling points. You do not need to memorize any of the KF or KBs. And the only melting and boiling point that you should know is for water. Normal freezing point or melting point is 0. Normal boiling point is 100. Normal just means at 1 atmosphere. So calculate the freezing point of a 2.6 molal aqueous sucrose solution. Well, we need the the freezing point constant for what solvent? Agua. Aqueous means water is the solvent. So we need, that's not what I need, we need to look at water. We know the normal freezing point is 0. The freezing point constant is 1.86 degrees Celsius per molal. So KF equals 1.86 degrees Celsius per molal. So the change in freezing point equals the molality times KF. Well, we were given the molality, 2.6 molal, and we're going to multiply it by that constant, 1.86 degrees Celsius per molal. 2.6 times 1.86. 4.836 degrees Celsius. It says calculate the freezing point. Is that the freezing point?
No.
No. That's the change in the freezing point. How do we figure out what the freezing point is? Well, you take the original freezing point and you go down this much, right? So the normal freezing point is 0, and really it's exactly 0 because it's defined that way. 0 degrees Celsius minus the change is going to give us minus, I'm going to round it off now, minus 4.86 degrees Celsius. Any questions?
What's the little m under 1.86?
This little m, or that little m?
That one.
This is the unit molal, moles of solute per kilogram of solvent.
What was that?
It's just a unit.
Nothing was there?
Mm-mm.
Ah,
It's a unit. So this is standing for molality. This is the molality. I hate molality.
that's the current unit.
Let's make our own unit. Yeah, too many people have already done that. Okay, boiling point elevation, same idea, but it changes the temperature, makes it higher. Okay, so the equation looks remarkably similar. We just have a B here instead of an F. Change in the boiling point, the molality times the boiling point elevation constant. Again, that's for the solvent. So antifreeze says it's against freezing, right? Antifreeze prevents the water in your radiator from freezing by lowering the freezing point of the water. Here in Fresno, we don't care about that too much because it just doesn't get cold enough for long enough that your your engine would actually freeze. In Minnesota, they care about this a great deal. It also prevents the boiling of the water in your radiator. We care a lot more about that here because it gets really hot in the summer and you don't want your radiator to boil over, right? So adding the antifreeze raises the boiling point of the water and lowers the freezing point. Awesome.
Why they only call it antifreeze?
Because antifreeze, anti-boiling over was probably too long. Yeah.
However much you're lowering or compressing the freezing point is how much you're actually increasing the boiling.
That's a good question. Is it the same amount? Does it depress the freezing point and elevate the boiling point by the same amount? We have to look at the constants. So for water, the freezing point constant is 1.86. The boiling point constant is 0.5. So it's not going to go up as much. Carbon tetrachloride, look at that, 29 and only 5 over here. So generally the boiling point is affected less than the freezing point, but some of them are more similar, like chloroform. Chloroform's pretty similar.
That one's pretty good.
Yeah. That'll knock you out too.
It's a good solvent too.
Yeah, that's what all the spies use when they,
Oh, to put it-
handkerchief over the mouth and yeah, down you go. That's chloroform. I'm not going to do this one because it's the same idea as the last one. It's the end of the semester, I'm tired. Osmotic pressure. Okay, so we've talked about osmosis. Osmosis is the flow of solvent from a lower concentration to a higher concentration. I think of it as nature trying to even things out. It's like here I've got pure water and there I've got salty water, and we want to make them the same. The salt can't move through that semi-permeable membrane, only the water can. So the water will move over. Semi-permeable membrane allows some substances to pass, but not others. And your body is full of them. So this is an osmosis cell. So here we have a U-shaped tube. I used to just call them U-tubes, but yeah, that's something else now. And there's a semi-permeable membrane. That wasn't funny at all. There's a semi-permeable membrane in here. And so here we have pure water on this side, and we have a solution on this side. We'll just call it salt because it's easier. So salty water on this side. So you have water moving in both directions.